Hello everyone, thank you for joining me today. The topic we're going to discuss today with this short lecture is going to be a bit more on the topic of loads. And if this sounds familiar, is because yes, we did cover this previously. So without further ado, let's get to it. Lovely. Thank you so much for joining me. So if loads sounds familiar, is because yes, we've covered it before. If you remember, it was in topic 1 that we covered loads. We discussed dead loads, live loads, snow loads, wind loads, earthquake loads, and more. I'm going to provide you with a link at the description at the bottom for this topic 1, if you want to review it. It's going to be provided for you there. And if you remember, loads is just another word for forces in structural engineering. Well, I just want to, give you a reminder of what loads are all about. In general terms, your textbook distinguishes loads into two types. So-called gravity loads, because they act in the direction of gravity, which for you and me basically means directly down, but really more accurately it means towards the center of the Earth. So gravity loads are dead loads, live loads, rain loads, and snow loads because they act vertically. Non-gravity loads, or so-called lateral loads, are those loads that do not typically act in the vertical direction. So that includes wind, earthquake, and other types of non-gravity loads. Okay. Now, a reminder of what the units are when it comes to loads. We're going to go through the metric ones first, okay? And the first one that I want to expose you to is if a force is distributed over an area, so in the event of a kPa, as shown here, which is the unit for kilopascal, it's kilonewtons per meter squared, its translation. It's the kind of force that you would see, the kind of load that you would see, say, over a roof, right? That was a result of snow, or over a floor, say, as a result of occupancy or the flooring itself. Okay, so that's an example of a load distributed over a surface area. Another one that you can think of is water pressure, right? If you take a submarine and you go underwater, water pressure is affecting that whole submarine all over its area. If we're looking at forces distributed over a length, an example of that would be forces that are then affecting a beam, right? Because it affects that beam only along its length. Well, the units for that in metric are typically in kilonewton per meter. So it's a force divided by a length, whereas a force divided by an area is for an area force. Lastly, just a straight force. Typically the units for that in metric are newtons or kilonewtons. And an example of that is forces that affect, say, a column, right? Because they go through a specific point. Or a bearing force. So say where a beam is supported by a girder. That contact is transferring a single force. The imperial equivalent to these metric forces are, for forces distributed over an area, PSFs, or pounds per square foot. Okay? If it's distributed over a length, it's pound per foot, or kip per foot, where kip is kilopound, so 1,000 pounds. And then when it comes to a single force at a single location, the units are typically pounds, or kips, where again, 1 kip is a kilopound, aka 1,000 pounds. Great. All of this, I want to remind you, is coming out more or less from chapter 3 of your textbook. So I recommend you review this, please. You read it over. It's not a difficult read. So more graphically, right, to illustrate these loads that I've just discussed when it comes to gravity loads, so loads that go vertically, okay, you get those kind of loads when they're affecting a whole surface, so like the floor in this case. And again, the units are in pounds per square foot, or in kilonewtons per meter squared, or kPa. Okay? So over a whole floor, that load is a surface load. Now, that floor is supported on beams. So that means that whatever load is on that floor, that surface load, it's transferred to the beams supporting it. And the only kind of load that that beam can take is a linear load, right? A force per length, like in this case, for this beam. So that's why it's in pounds per foot length, or kips per foot. Metric units for this are kilonewtons per meter. Then that beam is supported on columns, right? So that force per unit length then has to be transferred to individual columns. So then it becomes a point load, or a single force. And the imperial units on the force for this column, say, are in pounds or kips, or metric, they're in kilonewtons. Now, I want to talk a little bit more about some specific loads, and I want to start with rain loads. We're going to cover today basically loads due to nature, if you will. Rain loads, okay? They're caused by nature, and they're typically gravity loads, so that means they go directly down, vertically. 4.1.6.4 is where you'll find information in the building code related to how it looks at rain loads. So that's Division B, Part 4. Okay, and it directs you also to a table in the Supplementary Standards SB1 in your Volume 2, Climatic and Seismic Data. Right here, you'll find rain-related information that is cataloged by location, alphabetically cataloged by location. Okay, by various cities and towns in Ontario. Now, when it comes to rain loads, they're quite special because the more you put a rain load on, say, a flat roof, the more that flat roof takes a rain load. What I'm getting at is this. Pretend that flat roof is a trampoline, very springy, okay? And you start pouring water, like rain, on it. Well, that trampoline starts to sag. So suddenly, that trampoline, because it's sagging, or that roof, because it's sagging, it takes more rain load. That effect is called ponding, right? The more rain you put on a surface, the more it deflects, and the more rain it can take. So that's why ponding is an important effect on structures related to rain. And that's why flat roofs are actually not flat. Or I should say, properly built and legal flat roofs are not flat. They're actually sloped, even if just a little bit, so that you can direct water towards any type of dispersal system. So either drainage within the surface of the roof or scuppers on the sides of the roof to shed that water off of that roof. Now, here's the thing though, okay? You don't want to shed that water too quickly. That's why drainage management is important when it comes to rain loads. If you let the water off the roof right away, it will affect, well, as you can see here, passerbys, right? Maybe traffic. It might affect landscape, maybe the drainage and water infiltration around foundations and footings, but also it will overwhelm typically the sewer systems in the municipality you live in, right? So that's why typically proper roofs that are not sloped residential roofs, right? Large flat roofs are meant to retain water and slowly let it off, okay? I also did a little example for you that I'm going to link for you at the bottom in the description about calculating the rain load on a flat roof in Ottawa. Okay, it's a simple example just to give you an appreciation of how that is done. Snow loads. You're familiar with snow loads, right? We live in Ottawa, well, Canada in general, and many parts of Canada are affected by snow for so many months of the year. Okay, so 4.1.6.2 in the Ontario Building Code covers snow loads as a starting point. That's in Division B, Part 4. I recommend you check that out. Climatic data related to snow loads for the majority of cities and towns in Ontario are found in the Supplementary Standards SB1, Climatic and Seismic Data. And that's where you'll find S sub S, which is the snow load, ground snow load, and S sub R, which is the rain load that are used in the calculations of snow loads. And that's because, And I recommend you check this table out, okay, so you're familiar with it. So you use the rain load because it has happened in the past where it snows and then you get some rainfall and the snow sucks up the rainfall just like a sponge and makes things even heavier. Snow loads can be a somewhat complex affair, and that's because the snow loads on a roof are typically based on a lot of different things. They're based on the exposure of that building. So it makes a difference whether the building for which you're evaluating the snow loads is in the middle of a huge field or if it's in the middle of downtown Toronto. It makes a difference. It makes a difference whether or not there are obstacles on that roof, because obstacles tend to group snow loads around it. It makes a difference if that roof is sloped a little bit, sloped a whole bunch, or mostly flat. It makes a difference if there's a lot of snowfall, which you can find in SB1, if you get rainfall. But overall, it can be a fairly complex analysis to figure out the snow load on a roof, especially for large roofs that have lots of different levels and are kind of complicated. Okay? Wind loads. We're now moving on away from gravity loads, right? Wind loads, as you can see here, they're not a vertical affair. They can be, but they're not really a vertical affair. They're primarily horizontal. However, the right wind load, as you can see in this schematic I took straight out of your textbook, especially on sloped roofs, can affect those roofs by either pushing down on them or lifting them up. You know what I mean? Right? That's why sometimes you can lose shingles on a house if you have heavy winds, or you can get something like this, right? So although wind loads are meant to be horizontal, they can affect your structure or parts of it in a somewhat vertical direction, okay? You can find information about wind loads, and it's cataloged again alphabetically by town and cities in Ontario in the Supplementary Standards SB1, Climatic and Seismic Data. Okay, you'll find that information in SB1. And that's where you'll find wind loads for various categories for each city. Now, wind loads vary on a building depending on what the exposure or terrain is around that building. It's similar to snow loads in that the effects of wind loads on a building are different if that building is in the middle of downtown Toronto, very densely built, or if that building is lonely in the middle of a lake, right, with nothing around it. Building geometry is also very important. So what the geometry is of the building and how wind flows around it and over it matters. Roof slopes, as you can see, can matter, and also whether that building has openings. You see, when you have an opening in a building and you have heavy wind loads flowing into it, you can get a ballooning effect, right? So like you can see in this example, and this is an extreme example, this happens a lot, say, with barns or airplane hangars. When you have one big opening on one of the four sides of that building, and the remaining walls of that building have small or no openings, heavy winds that blow inside can kind of puff out that building. And that's something that must be considered when designing the structure of a building. Overall, it can be fairly complex, especially with large buildings or tall buildings. Okay, so that's why structural engineers spend a lot of time on this. Now, the final one, seismic loads. That's a fancy way of saying earthquakes. Earthquakes are not caused by giant dinosaurs walking downtown the city, right? What are they caused by? Well, they're caused by the shifting of tectonic plates on Earth, right? And these tectonic plates kind of rub against each other or move away from each other, or one goes under, one goes above. There's a lot of different things related to that. I'm going to link for you a video about how earthquakes happen in the description at the bottom. You can find information related to seismic loads in the Supplementary Standard SB1. And again, it's ranked alphabetically by city or town in Ontario. The seismic loads that affect buildings do so in a somewhat very complicated and complex manner. That is, the magnitude of that event, of the seismic load matters, right? So that's the strength, the energy released by that earthquake. The location matters, right? It depends on where you are in the world as to whether or not you'll be expecting to have higher or lower seismic events. The soil conditions that are around and under your building, your structure, matter. And interestingly enough, Ottawa, it's a seismic area. So if you design a structure for Ottawa, you must design it according to seismic requirements. So why do buildings fall down in seismic loads? The answer, hopefully not too surprisingly, is fairly complex. There's a lot of things that affect the building, seismically speaking. I'm going to link for you a video that actually explains that in very accessible terms, right? I thought it was a lovely video. It's a TEDx video that explains why buildings fall down, and it's going to be linked for you in the description at the bottom. What I would like to do now is kind of wrap up this somewhat more in-depth discussion of loads by comparing the effects of wind and seismic loads on buildings and how that affects building design. So I want to start off with wind loads. Okay, I'm showing both here, example of wind loads and seismic loads on buildings. As you can see for wind loads on the left of the screen, right, they affect the building. And the way that they affect the building, you may not realize this, is that they affect the envelope of that building. You see, what happens with wind is that as long as there is a building envelope covering the structure, then the wind pushes against the building envelope, and then in turn, that pushes on the structure. Once the building envelope is gone, the structure is no longer really affected, typically, by wind loads. That is not quite true when it comes to seismic loads. When it comes to seismic loads, the whole building and the whole structure participates in responding to that load, that earthquake. Even once part of the building starts to come off, like you can see here, it's still being affected by an earthquake. So those are the main things to look at, right? How the structure is actually affected by wind and seismic. And this is important because when it comes to wind, as we've seen, wind acts on the building envelope and then it transfers the wind force to the structure, because the envelope, the building envelope, is fastened to the structure. But once the building envelope is damaged or completely gone, the wind just flows through the structure, right? It flows through the building and it just starts to affect the interior of it. Now you can have ballooning effects, right? And that can be an issue. So typically, the way that you design structures for wind loads is that you plan for that structure to be able to resist the highest wind load and still be stable and strong and not be deformed, because that's affordable to do, okay? So basically, there should be no permanent deformation to whatever structure is designed, even under the highest loads. Okay? Now, it does matter what the importance factor is of that structure, right? So depending on how important that building is considered, there is a level, a spectrum of which deformation is expected or not. But typically, no. Highest wind loads, no deformation to the building, to the structure. That's not quite true for earthquakes. For earthquakes, they act on the whole building and the contents, even after the building envelope is gone. The idea is that with earthquakes, the building moves, the ground moves, and the interaction between the ground and the building and its content and how tall it is and how heavy it is and how the weight is distributed in the building affects that building's response to that seismic event, to that earthquake. So what happens with earthquakes? Well, different buildings are designed differently to resist smaller and larger earthquakes. Small earthquakes, the building is typically designed, the structure is designed to possibly be minorly affected. There might be some damages to the building envelope, maybe the flooring, roofing, wall, but the structure would be mostly intact. People get out safely. For large seismic events, although we do have the technology to build structures that can resist those seismic events, huge earthquakes with no effects, we can't afford it. So instead, buildings in seismic areas are designed to resist those large earthquakes enough to get people out, but they're likely going to suffer permanent deformation. So that building either has to be repaired extensively or demolished and rebuilt, right? So that's the big difference between wind and seismic effects on a building. It's affordable, typically, to design a structure so that it can resist even the highest wind load. It is not affordable to resist the highest earthquake and have a building that will also allow people to get out. So instead, you design that structure so that it may deform as a result of the seismic event of the earthquake, but at least people get out. Okay? And that's again assuming that the structures are designed legally, correctly, and properly. Okay? So that's the thing about seismic effects. Because it's just unaffordable to design a structure to resist even the highest earthquake without effects, it's not done, right? And you remember that falls under the limit states. Remember that third unofficial limit state you won't find in any building code? That's where it comes into play. All right, I'm going to recommend you check out Chapter 3. Read it at least to be familiar with the terminology related to these various loads. Okay, that way at least you're familiar with it. That's about it. And we've come to the end of this topic. I want to thank you so much for following along. You could have been anywhere else, but you've dedicated your time to this. Thank you so much, and have a lovely day.